Alright, I wanted to get a video out on this topic of inverse functions that we're looking at now. A lot of the functions that we're looking at have an inverse, and you've been using them the entire time you've been doing algebra, because whenever you think of trying to get something by itself in an equation, you have to think about the opposite, right? Dumb little equation like that, but you're going to get rid of the 4 by subtracting 4 from both sides. Well, that's an inverse, and it undoes that operation. Adding 4 gets undone by subtracting 4. So it's an undoing thing, but a more sophisticated way to think of it is that inverse functions switch the input and output. So what was input into the original function is output of the inverse, and what was output of the original function is input of the inverse. That's what's going on with the difference. So I want to work through a couple quick examples and think how this looks in terms of the equation, the ordered pairs, and the graph of them. Switching input and output in these few different ways of looking at it. So f of x equals 2x plus 5, a linear function, could be written if you use an output variable y equals 2x plus 5. Regular line with a slope there. If you think about switching input and output, you'd be switching from this one to the inverse. If I just symbolically switch the x and y, the input and the output variable, and go through and solve for what is my new function, my output now is y, this is the inverse function, but solve for y in this thing. I got x minus 5 equals 2y, so y equals x minus 5 divided by 2, or y equals 1/2 x minus 5/2. That's actually the inverse function of this one. Composing those would give you the identity back, or this is the inverse of that. Now if we put that on the graph, this is the graph of the original, started at, it had an intercept at 5 and slope 2, right? So every time it goes over 1, it goes up 2. The inverse function is y equals 1/2 x minus 5/2. So that goes through as a negative y-intercept down here somewhere, and it's going out with a slope of 1/2. That's over 2 and up 1, if you will. So it's not perpendicular to this. It's not that kind of relationship, but there is a relationship between the slopes. They're a regular reciprocal relationship. Inverse switches input and output, so it switches rise and run around. Or if you think of this as taking the original graph, switching the x and y, like you took that whole black line and you just crank the x and y axis to switch it around and sort of flip that around, this is what you get down here. It sort of wraps it around this way because it twists the x and y axis around. So that's how it looks graphically. Numerically, it's a real simple idea. My inverse function is going to have the same ordered pairs but the other way around. 5, 0, 11, 3, 15, 5. I just put some points of the original function. I just switched them around over here, and that's exactly what I've got. 5 zeros on the graph of this. 11, 3 would be out here, and 15, 5. Those are points on the graph of the inverse function. Great, that's a simple example. Those have a nice inverse there. Quickly, second example, power function started with y equals x cubed. Graph of y equals x cubed should be familiar. It looks something like this, right? Has that shape to it. Those are some of the points on that graph. If I symbolically do the inverse, find the inverse, you switch the x and y, and then you solve for this y here, because this is my inverse function, y. Well, that's easy to do on this one. It's to get y by itself, you got to do a cube root. So the inverse is going to be that cube root of x. What that cube root function, that's not as familiar a graph, but what that looks like is going to be, it's going to be this kind of shape. If you take the x and y and twist them around, this positive part's going to go this way, and this part's going to get turned around that way. That's what your cube root function looks like. F inverse of x is the cube root of x. It goes through points like 1, 1. Well, that point is on the graph of both of them. That's right there because the input and output were equal there, so switching them doesn't change anything here. But 27, 3. That's not going to get up to y equals 3 until way out there at 27. Negative 8, negative 2, because the cube root of negative 8 is negative 2. That's out here. So this one has negative 8, negative 2 on the graph, where the original function has negative 2, negative 8. And so you can do ordered pairs, you can do the graph of them, think them through that both ways. Now, bad example of that quickly. Functions where this doesn't work out great. Y equals x squared. Graph looks like that. If I twist around the x and y axis on this one, this is going up on either side of the positive y axis. If I switch x and y around, I'm going to switch that around and I'm going to have a graph that's going up or down on either side of the positive x-axis. Guess what? That's not a function anymore, right? We got a thing over there, but it doesn't satisfy the rule for a function of the vertical line test. Each input has two outputs. If I try to do this symbolically, I can switch the x and y and I get something. I get x equals y squared, but when I try to get y by itself, if you're disciplined at your algebra skills, you realize you get plus or minus the square root of x when you do that. You get two different things. And so the inverse is really not a function. And that's a problem because this wasn't a one-to-one function. That doesn't work nicely at all. So inverses work great on functions that are one-to-one, where you can turn them around and they still look like a function over here. The fact that this has two different points on the same horizontal line, that's okay for the original function, but when that gets switched around, that same fact there becomes two different points on the same vertical line, so that's why it becomes not a function. For those kind of things, if we talk about an inverse function, we can say this if we're only dealing with positive values in the original function. So if we only take, if I throw away this other half of it and only take the y equals x squared function where x is bigger than 0, then I can flip it around and I'm going to get half of that sideways parabola and I'm going to throw away that one. That works okay. So that's what we do if we want to talk about inverse functions. If the thing that we're starting with isn't one-to-one, sometimes we'll just narrow the domain of it down and take a piece of that, and then we can talk about the inverse of it, but it's limited by that. So that's not really a great example of a inverse function. I'll put up something about the complex numbers. That's what we're going into next. I'll put up something separately on that.